Hello everybody, this is Nick. Today in this video we're going to deal with how to design and specify solar panel systems. So let's get started. Well, first of all, let's state the problem. We work for an oil company and they have a facility down 50 miles south of San Antonio, and there's no available commercial power, so we're going to have to, our charge is to design a solar system to supply this facility. So let's start with the sun. Alright, so the sun over here is casting its flux down on some solar panel. Alright, and we're going to start with this thing at 90 degrees to it. And how much energy is the sun throwing off? Well, it turns out quite a lot. It turns out that the sun at the surface of the earth puts out about 1,000 watts per meter square. That's a lot of power. The bad news is our solar panel is only 15% efficient. All right. Now, I want to talk about a phenomenon. As the sun transits in the sky and it moves going up, is it no longer is it 90 degrees to the solar panel. There's some angle here, theta, and it turns out that the energy that we can recover from the sun is a function of cosine of that off-point angle. All right. We will need that data shortly, know about those angles shortly. So now let's talk about the load. All right. So you got a boss, perhaps he's not an Aggie, maybe he's a IT puke, or worse yet, a bean counter. So we describe the load by the power it consumes, and the units that we normally deal in power are watts or kilowatts. Today we're going to talk about watts. Right now, we also need to know how long that load is going to run in time, and I tend to use hours. You use anything you want, and the interval which I like to calculate over is a day, and you'll see why later. And then we need to calculate the energy. All right. Now the energy, watts of the energy, if you've been paying attention to Dr. Moore's class, is the power it consumes in watts over the time that it consumes it in hours. And that unit is referred to as watt hours. Okay? So now let's start to describe the load. Your boss tells you, look, I got some kind of widget over here, and it's widget A, and it consumes 10 watts. And I'm going to keep it running all day. So I'm going to run it 24 hours a day. And I got some load B over here, might be a radio, and it consumes 15 watts. And it's got to be on all the time. And I got this pretty big load. It's 50. Load C could be a pump, and it's 50 watts, but it's only going to be running half the time. Okay? So now we need to calculate the energy consumed. Well, it's just the product of these two numbers. So if it's 10 watts at 24 hours, that's 240 watt hours. The other one is 15 times 24, that's 360 watt hours. And 50 times half the time, 12, turns out to be 600. All right, and if I just go add all this up, this turns out to be 1,200 watt hours consumed every day. And the instantaneous load with everything running is 75. We're going to need this number later. All right. So now we've got to go figure out how big this solar panel is. Well, we know two things. We need to know two things. We need to know how big the solar panel is and how many hours is the sun overhead. Well, we're very lucky. The government spent a lot of money and they made this data public to us, so we're going to go to the web and look it up. So the first thing we're going to do is we're going to go Google PV watts. You click the first one that comes up. You see this site up here, and you scroll down to the map. We know we're in Texas, so we click Texas. Our closest town that the government has data on is San Antonio. We're going to click that. Now, two interesting numbers here. One is the compass direction that the solar panel is headed. I think we just kind of intuitively know that if we're in the northern hemisphere, we want to point it south, 180 degrees. What's not so intuitive is that the average optimum angle to tilt your solar panel, it turns out to be the latitude. Well, San Antonio is 29.5 degrees, so we will point it there. We scroll down here to the calculation button, press those arcs, comes up a set of numbers that are very interesting and useful. The first column is the month, starting with January through December, and this number, the columns in this number, is the average days, the average hours that the sun shines in a day. So, for example, we know in the winter the sun in a clear day is overhead about, maybe 10 hours, 8 to 10 hours. But remember, it's not exactly 90 degrees to our panel, and we can average, we can make an average, and this number is 4.10 hours. So now let's save this number, and we're going to use it. So let me switch back to the whiteboard here, and I'm going to go write this number down. Is that the sun hours is 4.1 hours a day. That's the average over 10 years. Okay, now, since we know the sun doesn't shine every day, as engineers, we got to make our best guess at how many days the sun is not going to shine. Well, in our shop in South Texas, we've looked at the data over 10 years. Our best guess for our conservative customers, if we choose 5 days of no sun, you can tell your customer that you will see less than one failure every 10 years. We don't expect this to happen but once every 10 years. All right? So how much energy does it require? How much energy do we have to store in that battery for 5 days? Well, we already know that we're consuming 1,200 watt hours a day, and if we want 5 days, that turns out to be 6,000 watt hours our battery has got to hold. All right, now let's talk about batteries. All right, so we start out, we know we need 6,000 watt hours in our battery to run this for 5 days with no sun. But also we know that batteries are not 100% efficient. We know that sometimes some of the energy as we try to stuff this thing in is going to escape in heat. So we tentatively think about batteries as 90% efficient. Right? So we're going to derate that battery by 10%. That turns out that we now need a battery of 6,666 watt hours. All right? Now, as engineers, you have to decide what's reasonable to recharge that. We just can't have a panel just stuff back all this in one day, but we're going to have to save up a little every day, a little rainy day deal to stuff it back. So we got to decide how many days we want to take to charge it back. Well, our company believes that 10-day recharge time is reasonable. So we got to put back 6,666 watts, and it's going to take 10 days. We're going to try to put back 660 watt hours. Okay. So our total panel per day now has got to put back our daily average of 1,200 watt hours plus 666 watt hours. So our total panel has got to now collect 1,866 watt hours. We'll pick it back up on the next video.